Have you ever wondered if you could create light from pure darkness? Imagine standing in a place where there is absolutely nothing. No stars, no lamps, not even a single photon. Just endless, infinite blackness. It seems impossible that anything could emerge from such emptiness, let alone something as vibrant and energetic as light itself. Not by flipping a switch or using any ordinary source of electricity or fire, but by pulling it straight out of what we thought was absolute nothingness. This isn't science fiction, it's a real phenomenon that scientists have only recently begun to understand and even demonstrate in the lab. It sounds impossible, right? But the universe at its smallest scales is full of surprises. When we zoom in far enough past atoms and even subatomic particles, we find a world that defies our everyday logic. A world where the rules are written by quantum mechanics. Recently, scientists managed to coax real particles of light, photons, out of the vacuum of space. They didn't use a bulb or a battery. Instead, they used the strange properties of the quantum vacuum itself, a place that seems empty but is actually teeming with invisible activity. They took what we thought was empty and made it glow, challenging our basic understanding of reality. This experiment didn't just create a spark, it lit up a whole new way of thinking about the fabric of the universe. The secret? Quantum mechanics, a realm where emptiness is never truly empty. Even in a perfect vacuum, the laws of physics allow for tiny fluctuations, brief moments where energy appears and disappears, creating what we call virtual particles. Down here, particles can pop in and out of existence and nothing is ever truly still. The vacuum is alive with potential, a restless sea of energy just waiting to be tapped. These virtual particles are usually invisible, but with the right experiment, they can be coaxed into becoming real, observable light. This discovery is a testament to human curiosity and our drive to understand the universe. It took years of collaboration, cutting-edge technology, and a willingness to question everything we thought we knew about nothing. So how did they do it? We'll explore the quantum vacuum, virtual particles, and the ingenious experiment that turned theory into reality. We'll break down the science behind this mind-bending achievement and see how researchers managed to turn the emptiest place imaginable into a source of light. We'll see why this matters for science and what it could mean for our future. Could this discovery lead to new technologies or even change our understanding of the universe itself? The implications are as vast as the cosmos. Get ready to explore the edge of what's possible. Let's dive in. The journey from nothing to light is just beginning, and you're about to witness the incredible story of how science can illuminate even the darkest corners of reality. When you picture a vacuum, what comes to mind? Maybe you think of a high-tech laboratory where scientists use powerful pumps to suck every last molecule of air from a sealed chamber. Or perhaps you imagine the vast, endless blackness between the stars. A place so empty, so silent, it seems almost impossible that anything could exist there at all. Most of us picture outer space as the ultimate void, a cold, dark expanse where nothing stirs. For centuries, this was the prevailing view, even among scientists. The emptiness between the stars was thought to be a perfect vacuum. No air, no dust, no particles, just pure, unbroken nothingness stretching for light years in every direction. Early experiments with vacuums in the 17th and 18th centuries reinforced this idea. Scientists like Otto von Guericke and Robert Boyle built elaborate devices to remove air from glass spheres, marveling at the strange effects of emptiness. They believed that, if you could remove every last atom, you'd be left with a true void, a place utterly devoid of matter or energy. But in the 20th century, quantum mechanics turned this idea on its head. Physicists discovered that even in a perfect vacuum, space is anything but empty. Instead, it's alive with invisible activity, a restless sea of energy and possibility. This is what scientists call zero-point energy, the lowest possible energy that a quantum system can have, even when it seems like nothing is there at all. To understand this, imagine a perfectly still pond. To the naked eye, the surface looks calm and motionless. But if you could zoom in with a powerful microscope, you'd see that the water molecules are constantly jostling, vibrating, and moving. The quantum vacuum is like that, seemingly empty but actually teeming with fluctuations and energy at the tiniest scales. In fact, space itself is more like a trampoline than a blank stage. Even when nothing seems to be happening, the fabric of space-time is always under tension, always rippling with tiny disturbances. These quantum fluctuations are happening everywhere, all the time, creating a dynamic, ever-changing backdrop for everything in the universe. The universe's fundamental fields, like the electromagnetic field, are never perfectly still. Even in the deepest void between galaxies, these fields are alive with energy, constantly shifting and interacting. So the emptiness between stars is actually a vibrant, energetic place, filled with potential and possibility. Physicists sometimes call this restless activity quantum foam. It's the true baseline of reality, the foundation from which everything else emerges. Every star, every planet, every living thing is built on top of this bubbling, energetic sea. Without it, the universe as we know it simply couldn't exist. Today, scientists are still trying to unlock the secrets of this not-so-empty emptiness. By studying the quantum vacuum, they hope to answer some of the universe's deepest mysteries, like why there is something rather than nothing, and how the universe first sprang into existence. In fact, recent experiments have even shown that it's possible to create real particles of light, photons, out of the vacuum itself, simply by manipulating these quantum fields. So, the vacuum isn't empty at all. It's the source of everything, the hidden engine that powers the cosmos. As we peer deeper into the fabric of space, we're beginning to see just how much is bubbling beneath the surface. Let's dive in and explore the wonders of the quantum vacuum together. So, what's causing all that quantum fizz? Enter virtual particles. These are pairs of particles and antiparticles that pop into existence for a split second, then vanish. Thanks to the Heisenberg uncertainty principle, the universe can borrow energy to create these pairs, as long as it pays it back instantly. Virtual particles are everywhere, all the time, even in your living room. They're called virtual because they're too fleeting to detect directly, but their effects are real. They subtly shift atomic energy levels and influence fundamental forces. Scientists have measured these effects, confirming that this ghostly dance is part of reality. The big question, could we ever catch one of these phantom particles and turn it into something real? That's where the breakthrough begins. The universe is filled with virtual photons, potential sparks of light that vanish almost instantly. These ghostly particles are everywhere, flickering in and out of existence within the quantum vacuum. They're not quite real, not quite imaginary, just brief possibilities, constantly bubbling beneath the surface of reality. In the vast emptiness of space, these virtual photons are always present, but they're so elusive that we can't see or measure them directly. They're like whispers in the cosmic background, hinting at the strange and unpredictable nature of the quantum world. The challenge is profound. How do you turn one of these fleeting virtual photons into a real detectable photon? One that you can actually measure and study? Scientists have spent decades trying to answer this question, developing ever more sensitive detectors and ingenious experiments to catch even the faintest glimmer of light. The quest to capture a ghost particle is at the heart of modern quantum physics, pushing the boundaries of what we can observe and understand. The trick isn't to catch the particle in the traditional sense, like trapping a firefly in a jar. Instead, you have to change its environment so quickly and dramatically that the virtual photon doesn't have time to disappear. It's a race against the clock, manipulating the very fabric of the vacuum to coax a particle into reality. This requires not just precision, but a deep understanding of how quantum fields respond to sudden changes. If you jolt the vacuum just right, by injecting energy at exactly the right moment, you can give a virtual photon enough of a push to become real. It's like flipping a switch in the quantum world, turning a possibility into a tangible event. This process is delicate and requires perfect timing, but when it works, it reveals the hidden potential of the vacuum itself. Imagine shaking a dusty rug in a sunbeam. The dust is always there, clinging to the fibers, invisible until you disturb it. When you shake the rug hard enough, the dust flies free, catching the light and becoming visible. In the same way, the quantum vacuum is full of virtual photons, waiting for the right disturbance to set them loose. In this analogy, the rug represents the quantum vacuum, and the dust particles are the virtual photons. Just as the dust needs a jolt to become visible, virtual photons need a sudden change in their environment to become real, observable particles of light. This simple image helps us grasp a process that is, in reality, governed by the most complex laws of quantum physics. But here's the catch. The shaking required isn't gentle. It's an extreme, almost unimaginable disturbance. One that involves changing the properties of the vacuum at a speed close to that of light itself. Only with the fastest, most advanced technology can scientists hope to create the right conditions for this transformation. This idea, known as the dynamical Casimir effect, was long thought to be impossible to demonstrate in practice. For years it remained a fascinating theoretical prediction, a mathematical curiosity that seemed beyond the reach of experiment. The equations describing it are complex, and the technical challenge is immense. But with the advent of clever quantum electronics and superconducting circuits, scientists finally found a way to simulate the effect. By rapidly changing the electrical properties of these circuits, they could mimic the extreme conditions needed to turn virtual photons into real ones. This breakthrough opened a new window into the quantum world, allowing researchers to observe phenomena that were once purely theoretical. Here's how they did it. In the next section, we'll explore the ingenious experiments and cutting-edge technology that made it possible to catch a ghost particle, and what this means for our understanding of the universe. The dynamical Casimir effect is the key to making light from nothing. Normally, the Casimir effect uses two mirrors in a vacuum, creating a force by limiting which virtual particles can exist between them. The dynamical version needs just one mirror, but it must move at a significant fraction of the speed of light. This rapid motion jolts virtual particles, turning them into real photons. For decades this was only theory. No machine could move a mirror that fast. The breakthrough? Use a virtual mirror, a point in an electrical circuit that acts like a mirror for electromagnetic waves. By changing its properties incredibly fast, scientists could simulate a mirror moving at light speed, without moving anything physical. This shifted the challenge from mechanics to quantum electronics. Suddenly, the impossible became achievable. The stage was set for a revolutionary experiment. Let's see how they built it. Instead of a physical mirror, researchers used a superconducting circuit cooled near absolute zero. The heart of the device was a SQUID, superconducting quantum interference device, acting as a mirror for microwave photons. By rapidly changing a magnetic field, they could shift the SQUID's properties at incredible speeds. This simulated a mirror moving at 25% the speed of light, fast enough to jolt the quantum vacuum. As predicted, the circuit began to glow. Real microwave photons appeared seemingly from nowhere. The photon's properties matched theory exactly. For the first time, scientists directly observed the dynamical Casimir effect. They had created light from the energy of empty space using pure quantum engineering. It was a triumph decades in the making, but why does it matter? Why should we care about a few photons in a lab? This experiment proves a fundamental prediction of quantum field theory. The vacuum is alive with energy. It deepens our understanding of the universe's foundations. The physics is similar to Hawking radiation, the process by which black holes might slowly evaporate. Studying this effect could unlock secrets about black holes in the early universe. It also opens doors to new quantum technologies like unique light sources or ultra-sensitive sensors. Creating particles from nothing connects the tiniest lab experiment to the birth of the cosmos. It's a profound leap in our quest to understand reality. Did scientists just invent a free energy machine? Not even close. Creating photons from the vacuum took a huge amount of energy, far more than the light produced. The energy came from the equipment, not the vacuum itself. Think of shaking a rug. You have to put in work to get the dust off. The effect is tiny, just a handful of photons, detectable only with ultra-sensitive instruments. This isn't a new power source but a proof of principle. The real value is in what we learn about the universe. Like Faraday's early experiments, today's discovery could lay the groundwork for future breakthroughs. For now, it's a fundamental insight, not a practical technology. The future is wide open. What does this discovery mean for us? It's a testament to human curiosity and ingenuity. We've gone from myths about darkness to building machines that reveal its true nature. This journey, from wild theory to a flash of light in a lab, shows our relentless drive to understand. Every discovery, no matter how small, adds to the grand puzzle of existence. Creating light from the vacuum illuminates not just physics, but the power of the human mind. The universe is stranger and more wonderful than we ever imagined. There are still mysteries to solve. Dark matter, dark energy, the origin of life. Our journey of discovery is just beginning. The darkness around us is full of potential, waiting for the right nudge to burst into light. And we're the ones who figured out how to give it that nudge.